Oop. Morning, everybody. Hear
Good
me
morning.
okay? Morning. You can see behind my green screen here. I'll let you see. Whoa. Um, Hope you folks are doing okay. I forgot to, or maybe I did mention last week. So I'm teaching another class, an undergraduate class at the same time, and sometimes I forget the announcements I make in different classes. But as you know, today is election day, and you are not required to be here now. And especially since the lecture is recorded, you'll have access to it. If you need to use this time to vote, feel free to go ahead. I just wanted to say that. It was recommended that it was actually recommended by some folks that we cancel class, but I thought since we're recording it anyway, we should be fine. But I just want you to know that before we get started. If this is the time you want to vote in the next 3 hours, go for it. It's no problem at all. But okay, other things. I think it's time for a midterm. What do you guys say? No? Michael says no. All right. All right, never mind them. Yeah, we have to take a test. So it's going to be very casual. The style of the exam will be casual in the sense that you can take it any time. Okay. So here's the deal. This is week 5, as I remember. Correct? This is week 5, kinda. We started the week on a Thursday, so I think this is our 5th lecture. I'm pretty sure. So we're about halfway through. And after today. And so this would be a good time for a test. And I think what I'm going to do is I'm pretty sure I'll be able to finish the half of the material today. And if not, it just will be a little bit at the beginning of next lecture. So I think the way to do this is to make the test available to you Tuesday night of next week, which will allow you to ask questions during Tuesday's class, Tuesday's meeting. And then you can take it. I don't know. It's up to you guys. I mean, I'm perfectly happy to let you take it any time between that Tuesday and the following Sunday. So if you wanted to take it over the weekend or something, that would be fine. The only problem with that is, you get your feedback a little later. I don't know if that has any bearing on a graduate class. It might really not. I know sometimes undergraduates like to get their first grades back early so they can decide whether or not to withdraw from the class. But I can't imagine that have a bearing on you folks. So I'm perfectly happy giving you 5 days to take it. And it would be a single period where you sit down and take it for 3 hours, but you can take it at any 3-hour block between Tuesday night and Sunday night or something. What do you guys think about that? I'm open to other suggestions, except Michael's suggestion, which is to not have an exam.
I do stand by that, but otherwise that sounds fine. Yeah.
All right. Anything else, Morgan? Is that actually? I know you folks have some statistics, but it's not as it used to be, which was very often we would have this exam around the same time as the statistics midterm. But I understand that Annie's doing it a little bit different in her course. So
I did have a question about the structure of the exam.
Yes.
Is it like short answer, multiple choice?
Yeah. Okay. So I'd be happy to talk about that. I will. What I have actually that I can post online is a blank version of the exam, which kind of shows you the different sections. So there are 4 sections. The first section is short answer, where I ask you basically for a brief definition of different terms. Okay, and I think I can't remember if I have 10 or 20 questions in there. I think it might be 20 different short answer that you give. The second part is a little bit more explanation, and I think that there's 10 of those. And I ask you to, briefly discuss in a few sentences, maybe how some finding relates to some term or something like that. The third section is half-page essay. I believe there are 4 of those. There you're going to explain and list parts of a concept and that sort of thing. And the final part is a choice of one of 2 essays. You'll be given a choice of which one you want to answer. And for that one, basically it's going to be a test of your integration. So it's not going to be something you'll be able to just, recite from, the class. I'll be asking you to kind of integrate concepts in the class that haven't necessarily been explicitly integrated before. And you can write for that answer anywhere between a page and 2 pages, whatever you feel comfortable. You're certainly never graded on length. You're graded on completeness, so that's something to consider, but it could very well be that you can be complete in your answer without writing more than a page for those. And I'll also show you the breakdown of points, so you know how much time to devote to the different sections. Okay, so it's an intensive exam. It's testing pretty much everything from the first half of the course, but you're allowed to do it in a relaxed, more or less context. It is closed book. I don't want people using their notes for this, so I do want you to really study so you can do this from your understanding and your memory. And then I think we discussed this a little bit. I can set it up so it submits on its own on iLearn, but I think it might just be easier for you folks and less pressure for you to have a doc, for me to send you a Microsoft Word document and for you just to fill in your answers there, and just we'll go by honor system that you took 3 hours. And I have a little blurb in the beginning of the exam about the honor system, and then I have you sign it. So, okay, so yeah, it's long, it's comprehensive, it's there's a lot of information, but if you study hard, and feel free to study together. In fact, this is the sort of exam that if you folks can pull off a couple of Zoom meetings and meet and talk, discuss the concepts, it would probably help a lot. And in a course like this, where there's concepts, theory, philosophy, it really helps you to be able to explain the concepts to other people. And sometimes it even helps. I tell students in my undergraduate courses that if you can explain it to the layperson, so explain it to your parents, your grandparents, your friends that aren't taking the course, in a language of your own, so that they understand it, that really shows understanding. And you probably know about these findings, but there's a very nice literature in the educational psychology field where if 2 groups of subjects are asked to learn material in order to take a test on it, or learn material in order to teach it, and it's the same material in both cases, and then both groups are given a test, the group that actually studied for the purpose of teaching does better than the group that actually studies for a test per se. So imagine yourself, as you're studying, whether you do this for real or not, being able to explain everything. Like, okay, I'm a TA, I've got to go in and explain these concepts to undergraduates who know nothing about this. If you can do that thoroughly in a language that you're comfortable with, and you believe they would be comfortable with, without jargon, or if there is jargon, you can explain the jargon, then you're going to do well. So yes, if you can get together and do a little a review session where you actually try to explain the concepts to each other, it's going to help immensely. Other questions? Okay. I'm sure that there will be other questions next week, and I'd be happy to answer those on Tuesday. I will post the kind of bare bones outline of the exam on iLearn. I can do that tonight, so you get an idea of how many points each section is worth. That's fine. But I think once I send you the exam, which would be a week from tonight, at that point, let's see. I don't know. I feel kind of, well, I would certainly, I could answer questions. Now, I think once I send you the exam, actually, I think this is important. Once I send you the exam, I'm not going to answer questions on this material again, okay? Because it could be, I don't want to favor folks that wait to the very end if someone wants to take it early or something like that. So it's best that you go through your notes this week. We have a full week to do this, and I'd be happy to answer any questions next Tuesday. Once I send you the exam Tuesday night, then let's wait on questions until after everybody completes the exam by the following Sunday. Okay? So it does make sense for you to look through your notes this week. Sound good? It's we used to do this exam in class, and the rules were very different. But I actually like this because it doesn't take away class time, which is really useful for me to be able to teach even more material to you. So you're getting your money's worth. Okay, then certainly we'll talk about this more next week. Feel free to email me any questions, or we can set up a Zoom meeting if you want between now and next Tuesday. It just makes sense for you to study now, to start looking through your notes now. And you will have 95% of all the material you'll need by the end of today's lecture. We might have a little bit to do next week, but hopefully very little. And then I'll say, okay, at this point during my lecture next week, after the first, say, half hour, that's everything for the first exam. Now we'll go to new stuff. And so the second, 2/3 of the class next week will be on material for the final exam. Okay. Okay. Any questions on anything else about the course, the midterm, anything else? Is that? So I looked up fall for backgrounds and it gave me that. Are those leaves behind me? Are they changing color? I can't tell. No? Okay, so it's not really fall. Well, I think I have a couple of backgrounds that are very fall, but it shows leaves kind of coming at me like I'm being pummeled. And I think that will be distracting. So this seems a little bit more relaxing. But if you want something more exciting, and the undergraduates do, the undergraduates want roller coasters behind me and stuff. I find that a little distracting, but I guess they're used to distraction, the undergrads. So we'll stay with this for now. Okay, then let's continue talking about where we left off. And I believe it's hard having class once a week. Sometimes it's hard. I had to go back to my video. I believe we were about here. I think we talked about the McGurk effect, right? And then we talked a little bit about the features for phonemes and why it was so difficult to design a machine that could recognize speech based on it looking for the critical features. And the real upshot of this is the critical features change with context. So I think that the analogy that works for me is that it's very unlike a text reading machine or the check reading machine or anything like that, where there are very clear items like letters and then features for those items, even if there's different fonts. Here you have segments, in this case phonemes for speech, which are actually smushed together in the signal. And so the phonemes that follow and precede the target phoneme that the system's trying to understand are influenced by what's before or is influencing the target phoneme. But more than that, it's like the target phonemes are actually overlapped. And that's why it's been so difficult. And it really has to do with this co-articulation, the fact that in fact we are producing multiple phonemes at one time. I should mention a tiny bit more about co-articulation. It's not just the case that it's the adjacent phonemes that affect the phoneme that's in question. Okay, so as I say co-articulation, there's a good example. Let me just mark this. When I say co-articulation, sorry everybody, just give me a second here. Oh crap! Oh, shoot. There we go. Okay, just so it looks good on the video. I know you guys are using the videos. I saw the views. So for co-articulation, not only is it the case that in this example, for example, the ka and the a would be affecting the o, but also in some cases, in many cases, it's a couple of segments, it's a couple of phonemes away that can affect the o. So when you make the o in co-articulation, it's not only being affected by the preceding and the following phoneme, it's actually being affected by two phonemes down the line. And sometimes it can even be three phonemes down the line, depending on the combination. So it's not like just, adjacent phonemes are kind of overlapped with each other, but phonemes that are, two or away following or two away preceding can influence it. And that's, again, kind of demonstrating the mess that a speech reading machine has to contend with, as does our brain. Okay. Now, there's before we go ahead and talk about a theory that was designed to address how this might work in the brain, I wanted to give you one other example. And this example is one that I hadn't used for a while because the demonstration wasn't very good. And in fact, the demonstration doesn't work now at all. But I wanted to give you the concept because I think it's important. So let me skip ahead. And I think I already did all the McGurk effect stuff. Yeah, so let me go to this. Yeah, we know. Duplex perception. Okay. So here's the idea of duplex perception. This is nice. I'm glad I at least set up the slide because just to remind you, this is what a normal spectrogram looks like. So this is for APA and ABA. Okay, and this is nice because now we can compare it to the schematic. This is just a schematic, so you can see what is often considered the critical features of speech, or the sort of thing you'd at least want to, get your machine to look for, which are these formant transitions. Remember, we said that ba and pa and ba and da can be distinguished to some degree by these transitions, but then we discussed the fact that those transitions are in fact dependent on the vowel context. But here we can see it. So this is pa and ba. And let's see here. It's a little messy. Let me see if I can find a better example for you. How about if we go with, let's go with ada. Yeah, good. Okay. So let's look at ada and aba. Okay. And these are the transitions here in the actual acoustic energy that are being represented in this schematic. Does that make sense? So as you look at what's called the first and second formants, which are these smudges, these kind of high density energy bands here, you can see that for duh, the first formant transition is rising and the second formant transition is descending. And that's exactly what's being portrayed here in the schematic. Okay? For ba, on the other hand, and it's not completely clear, but if I was able to kind of zoom in, this is the first informant transition here, and it is the case that both of them are ascending a little bit, and that's what's being portrayed here in this schematic. So that's just first a way of seeing how the schematics relate to the actual energy as it's plotted out on the spectrogram. Just a quick review, the spectrogram is nothing but time, so it's pa and ba as it goes across the horizontal axis. And here's frequency across the vertical axis. So these are really high tones here and really low tones there, but it's a much wider range than my voice just portrayed. And the darkness of the smudges is representing how much energy there is. It's the acoustic intensity. Okay, so this is just formant transitions here, here, and here they are schematized so you can see them more clearly. Okay, now what we can do, since we have some sense that these are at least related to features, even though they're not going to be consistent features, we can start actually synthesizing speech using these features and start playing with them to try to figure out what's going on. So there, lots of ways of synthesizing speech. You probably have some sort of rudimentary speech synthesizer on your computer somewhere. We have a bunch in the lab. In the old days, they would do it in very fun kind of more physical, less digital ways. But they were able to do it so that what they could do in the speech signal is actually take out a critical formant transition. Now, I'm going to have to talk through this. Unfortunately, these demonstrations don't work anymore, and it was never a very good demonstration anyway. I don't think people found that it was synthesized speech, but it was syllables, and they were old school synthesis, so it wasn't a great demonstration. But what you can do basically in synthesis is remove a critical transition. And I think these were, what were they, Bez or Des or something like that. And what was it? Yeah, dag versus ga or something. And what you can do is, this is the first formant, so this is the one down here. This is the second formant, the one here, and the third formant, which I think would be right here. And sometimes it's the third formant's transition that distinguishes one phoneme from another. In this case, it would be de from ge. And so if you took out that, quote, critical transition, okay, it would be something neutral. If you had a rising transition in this context, it would sound like a ge. If you had a falling third formant transition, it would sound like a de. But if you took it off, it would sound something like a re, or something very kind of ambiguous, not clear, it would not sound either like a de or a ge. Okay. This is where I would normally play it for you, but it's not critical that you hear it as long as you get the idea. If we had this type of transition in based on the synthesis, you'd hear a ge. If we had a descending transition, it would sound like de. If you had no transition, it would be neutral. Okay. So what we're doing here is we are, yeah, that's what I wanted to put. We're separating a critical transition from the base. Okay, so this is the transition that can act like the critical cue in this context. Remember, it's very, very amorphous in the sense that as you put another vowel context there, it's going to sound, the transition and how it works is going to be different. But for this particular vowel, be, de, this is where the critical transition seems to lie. Okay, so you're going to separate the critical transition from the base, and what I mean base here is everything but the critical transition. So it would look like this. Okay, we took it out, and it's going to look like this. And now I could play it for you, and because it doesn't have that critical transition, it would sound like nya, nya. There he is. Kind of sounds like an old Yiddish guy complaining. Yeah. Okay. So it's missing the critical transition. You now no longer have a ge or a de. It's something that's ambiguous in between them or whatever. Okay. Now what you do is you take one of those critical transitions, and there's two ways of doing this. Either you can put it to the other ear. Okay. So the base would go to this ear. So everything but the critical transition would go to the right ear, and the critical transition would go to the left ear. And this is actually the best way to do it. There's tons of research on this, doing it this way. But the demonstration I would ultimately play, and I will be discussing today, actually has another way of doing it. And the way you do that is you can play the bass to both ears and then play the transition to both ears, but manipulate the transition separately from the bass in terms of how loud it is. And let me describe what happens when you do that. So you're going to, this is all done with synthesis, and you can, put the recording of the bass, through one channel of what both ears are hearing, and the separate transition you can manipulate separately as they're coming to both ears. So it's no longer, bass to one ear and transition to the other ear. But you can slowly increase the intensity of the transition. You can make it louder a little bit at a time. And here's what happens when you do that. Okay, at first, because it's so quiet that, okay, critical transition. And I should say, let's just choose the ga one to play first. But we're going to make it really, really quiet. Okay, and we're going to play it very quiet where the bass is loud enough to be recognized, and it's going to sound like nya, nya, nya. But very slowly, we're going to increase how loud that transition is. And at some point, the nya is going to change to a ge. Okay, because we're increasing the energy of the transition. And now these things are being perceived together. Okay, so this is loud enough now. This little baby transition in here is loud enough to kind of integrate with the bass. Okay, and it sounds no longer like a nya. It sounds like a clear ge. Okay, makes sense? You hear a clear syllable. You could also do the same thing with the da, and it would go from nya to da. And you can ask people what they hear. There's lots of ways of designing these experiments. They're done rigorously. I'm kind of describing it intuitively, but they're done rigorously. But then as you increase that transition, so the intensity is louder still, not only do you hear an unambiguous ge syllable, but you hear that syllable along with the transition itself. So here's what you're hearing. At first, with a very, very quiet transition, you just hear the neutral bass sound. It's nya, nya, nya. As you then increase it, it turns into ge, ge, ge. Okay, I say it's ge. I say it's ge. And then as you increase it still, you hear ge, and you also hear the transition itself. What does the transition itself sound like? You know, you're not going to believe this, but I have a way of showing you through a duck call. I just got this, and I realized this sound, I didn't notice this just a second ago. This is what the transition sounds like. Okay, I love that sound. Do you like that sound? That's what the transition sounds like. So you hear ge, ge, and then after you continue to increase the transition, it sounds like ge plus this little transition sound on its own, which you would never say is a speech sound, right? It's clearly a speech syllable and something else. Okay, so that little piece there, that little transition is lending itself so you hear a coherent syllable, but then with this extra energy, your brain hears the transition itself. Okay, what does that mean? Well, this is interesting. Okay, this is sometimes called preemptiveness in this literature. And the idea is this, and this is really the point of me going through this demonstration to kind of set us up for the theory. The point is this: to the degree there might be a speech module, it's going to look for anything it can in the input signal to make a coherent, recognizable speech segment. In this case, it's ge. And then it's going to use that to disambiguate a syllable or disambiguate a phoneme, okay? And then anything that's left over, it's going to say, okay, I don't need this because I've already disambiguated my syllable. I will give this extra energy to the other parts of the brain that analyze sounds that aren't speech. So here comes the signal. Let's look at this figure down here. Here comes the signal. Here comes the input. And all of it goes to the speech center first. The speech module, if we want to call it that. It uses them, the speech module uses whatever it needs to establish a recognizable, coherent syllable. And then, if it has anything left over, it passes it to what we can call the general auditory module or the auditory processing of the brain. I'm hesitant to call it an auditory module. I think your reading does, but it doesn't have the same characteristics of a module we've been discussing before. So I would maybe change this to general auditory processing system or something like that. Okay, I think one of your readings calls it an auditory module, but it really isn't a module. It just passes whatever it no longer needs to the rest of the brain to decipher as a non-speech sound. And it really does sound very close to this. You're going to hear, so what you're going to hear through the headphones if I did this demonstration would be ga, ga. Okay, here, I can do this. I'm really enjoying using this, by the way. And by the way, I'm not a hunter. This is a turkey call, appropriate for Thanksgiving, I guess. I just love to collect sounds, natural sounds especially. So this is what you would hear, okay, as I increase the loudness of the transition. We're using a ga transition here. Nya, 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 ge, 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 ge. Okay. Actually, that's much better than the actual recordings I could have played you. Again, at first you hear just the neutral bass, then you hear, as the energy is increased, you hear an unambiguous syllable, ga, and then you hear that unambiguous syllable plus that little kind of, what would you call it, a squawk, a chirp? I mean, it's called a chirp probably in your papers. And the idea is the speech module is using whatever energy it needs, and then it's passing on the remainder of the energy, the acoustic input energy, to the rest of the brain to decipher in a generalized auditory processing system, okay, which processes all non-speech sounds. Now, the term preemptiveness is important here because what it suggests is not only is there a specialized speech module, according to this, but it's a speech module that kind of takes precedence, that whenever a sound comes in, the speech module kind of elbows its way into the front of the processing stream and says, speech is so important to us, brain, I'm going to do my analysis first. If I don't find speech, you guys can have it. If I do find speech, I need to make it a coherent segment, a perceived coherent segment. And if I have anything left over, like a squawk, you guys get it. And the you guys is just a generalized auditory system, auditory processing system, which deals with all types of sounds besides speech sounds. Okay, so let me make sure I've covered everything here. Yeah, I think I have. Are there any questions on this before we continue now? Because this is I know that we wanted to kind of establish, I think based on some questions you guys had last week, we wanted to establish how a speech module would, I guess, interface with the rest of the brain in analyzing sounds. From this perspective, at least, the perspective I'm about to unfold in detail, it is the idea that there is a special speech module, it deals with speech sounds, and it takes precedence. It preempts the signal such that it looks for speech first and then passes anything else that it doesn't need up to the rest of the auditory processing system, okay? It is why, and faces, by the way, work in the same way. This would be, some of the support you see for these sort of modules, the preemptiveness of the module, would be that this is why you hear speech in sounds that aren't speech, like a hairdryer. This is why you see faces in things that aren't faces because of preemptiveness. So let's just switch very quickly to a face module. The face module would look at a stimulus, see if there's anything about a face in there, and if it sees anything close to a face, we'll kind of interpret it as a face, at least initially, right? As it's electrical plug, boy, that has some face features. It's a silhouette on a mountain, oh, that has some face features, and that's why we see faces and things that aren't in faces, and that's why we hear speech and things that aren't speechy, because of that preemptiveness. Okay. Any questions?
I have a quick question.
Yes.
The duplex perception is just the act of splitting up.
I should have mentioned that. Yeah, thank you. I should have gone back to that. I meant to go back to that title. What duplex perception means is that a signal is being used in two ways at the same time. So that chirp, especially when it gets loud enough to be part of a critical transition and a non-speech chirp, it's being duplexed. It's being used as speech and as non-speech at the same time. And that has been used as evidence for a specialized speech module. Thank you for asking that, Hunter. That's I forgot that I had that term up there, and it's an important term that you understand. So when duplex perception, and also that term duplex perception is used, I think initially was used for speech, but it's also used for vision sometimes, where you can see a piece of a visual image as being part of one thing, but also separate from other thing. It's being part of something else. And so Gestalt has tons of examples where you see a blob both as part of a cat silhouette and as a blob in and of itself, that sort of thing. That would be an example of a duplex perception, but we'll just be using the term in the context of speech. So thank you for asking that, Hunter. Other questions at this point? No? Okay. Then let's continue and kind of formalize this theory. Here's the idea. Because of the mess, because of the kind of severe overlap in how we produce speech, because of co-articulation, we've talked about the possible ways a computer would do this, but how does the brain do this? And the idea here in this theory of speech perception that you'll see was very popular in the 80s and 90s and has gotten really popular again, is based on the idea that to disambiguate this mess of the speech input, we make reference to what the brain knows about speech production. And this is the motor theory of speech. Okay? You'll read some old papers about the motor theory, but there's certainly new papers on the motor theory. And you're going to see it has far-ranging implications for modern perceptual psychology. So the general idea is that speech is perceived using tacit knowledge of speech production. I'll explain that image in just a second. But the idea here is because of the mess, because of what co-articulation does to phonemes, the speech brain, the speech module, needs to kind of look to what it knows about how speech is produced in order to disambiguate the signal. Okay? So it needs to take into account how co-articulation is actually destroys or actually distorts the signal. So here's the idea. Here I am. Let's talk about this. This is Gary Sinise in a photo that was taken from the movie Apollo 13. I think most of us have seen this at one point or another, right? It's the Tom Hanks movie where they plan on, it was the third scheduled moon landing, and then there's this really severe accident in the lunar module, and they barely get down, but they do. One thing they show is something that they still do, which is basically, if it's an emergency, they try to recreate the emergency in a full-scale model of the space shuttle or the lunar module back then on the ground that they have in Houston. And if you ever have a chance to go to the Space Museum in Houston, it's phenomenal. And they have their model, the scale model of the lunar module there, where they actually did this. And the idea is just this. This is something that is done in many contexts, just not NASA. That in order to try to make sense of what's going on, there's a recreation of the problem and then how to solve the problem. And that is one way to think about what goes on according to this motor theory. That here comes this crazy, distorted, overlapping signal. And what the speech brain, the speech module, is going to do is it's going to try to recreate how the signal got that way, okay? Like recreating how the explosion on the lunar module happened. It's going to recreate how the signal got that way and then try to kind of solve it. How is it going to recreate it? By looking at other information in the module. So here I am. I'm a little homunculus in the lunar module, in the brain, in the speech module. Okay, I'm I'm kind of looking around for help. And in the speech module, there's it's a good thing it's been designed this way. There's a lot of things that actually can help me as this distorted signal comes in. So the speech signal coming in is co-articulation, but because of the way it's produced, and I have to determine what the segments are, there's so much overlap, I need help. So what I do is I look around my module and I look to see if there is something that can help me determine how that mess occurred. And there's my buddy, that the homunculus that's involved in speech production, as part of the speech module, that's going to say, hey, I can help out because I know how our co-articulation makes a mess of the signal. And so in other words, I'm going to use the knowledge I have access to concerning how speech is produced to help me kind of disentangle the input. I'm going to make use of motor knowledge. Okay. Now, this is where we're really kind of making contact with modern theories of perception and cognition. And I'm sure that some of you have heard these sorts of things before when it comes to concepts of mirror neurons and embodied cognition, that perception, cognition, maybe all of psychology is continually making use of the access it has, the access the brain has of how behaviors are initiated, how behaviors are put together. In this case, we're talking about speech behavior. So here is just a term, mirror neurons. We're going to talk about this in just about 5 minutes. A about what all this means here in this context is that the speech perception system is going to involve kind of neural machinery that's going to incorporate information about how the speech is produced, okay? So it kind of really changes things about the perceptual system here. And this is really important for the motor theory of speech perception. I kind of hinted to this before a little bit. Remember we were talking about the speech loudness, vocal effort effect? I said a couple of times when we were having that discussion that the speech perception system kind of bypasses its analysis of the superficial acoustic signal, okay? And what it wants to retrieve is something about the motor action, something about, in that case, the articulatory effort or the articulatory work that went into producing the speech. Okay, so that's what's primary for the speech perception module, right? Is to find what sort of motor actions produce the signal. And that's partly a consequence of the perception system having of insight to the motor system, okay? So it kind of changes what it's working with. It kind of changes its primitives. It actually, as I said, it bypasses the superficial acoustics and is kind of making its objects of perception, the things, its primitives. The perception system is trying to work with pieces that are really better conceived of as being tied to articulation and speech production than the superficial acoustics. And so the sort of comments you'll see here in papers that have to do with this is that we perceive speech production, not the acoustic signal. However, this is for speech, not non-speech. Okay? And so here comes the speech brain. Since it's making use, it has a kind of a language with its own speech production system. When the signal comes in, it ain't going to look very much at, it's not going to do a superficial analysis of all the details of the frequency and the intensity and stuff. Instead, it's going to be working with the information that's being provided about how the speech has been articulated. Okay? So that's something that is considered to be kind of specific to speech, which suggests that since it's working in a language, since the processing in the module is working in a language of speech production, all right, it's really dealing with primitives that aren't tied to hearing or seeing or touching. Sometimes these are called amodal primitives. These are pieces of what's being kind of computed. It's still a computational system in here. It's being computed, and these are more related to the production system than anything tied to just the acoustics, just the optics, or even the haptics, right? If we're talking about feeling speech. So this is what explains the McGurk effect, right? This is the sort of thing that explains the McGurk effect, that it works so well because in an important way, the speech brain doesn't care whether it's getting its information from hearing or seeing or even touching, right? And it's working to retrieve the articulation because it has this great access to how speech is produced, okay? Again, I've kind of hinted at this, but this, at least at that time, was considered special to speech. At that time, I mean, the papers you'll be reading from the 80s, the 90s. At that time, this was considered to be special to speech, that it was only for speech that we had access to the kind of the production mechanisms and the production details, so that speech was perceived different from every other sound because of that access. This was considered to be special to speech. And this is what kind of, I guess, defines it as a module. Okay, so we've discussed modularity in the context of it kind of having a different set of processes, including all those characteristics that we've been talking about, right? The amodal nature, it takes in information from every modality. The anatomical specificity, the lack of kind of awareness of what's going on, the cognitive impenetrability. It doesn't make really much difference what we know outside the module. The module kind of does its workings on its own. And it does so because of that kind of tight link between perception and production that exists inside that module. Also, it's this that allows, first of all, for speech perception to occur at all, right? Because the input is such a mess. Yeah, we have ways of doing this now computationally with Siri and, Alexa and all those. But as you know, even after all these years, it still doesn't work as well as the brain. It works so well in the brain, according to this approach, because of that access to speech production, okay? And so it also accounts for the efficiency, the fact that it works so quickly, so automatically. And that is kind of a prime example of a module, right? That modules don't need the general processing of the rest of the brain. It works in a different way, and that different way makes it super efficient, okay? And in most cases, super accurate, okay? So this, at this point, what we have here is kind of a prime example of a module whose workings are different from the rest of the auditory system of the brain, okay? And it does so by making contact with speech production. It brings that into its processing system, which makes the things that it's working with really amodal. It really is working with, I guess, hypotheses of how the signal was produced, what production went into the articulation, or what kind of how the co-articulation occurred based on the production system. So it's really working with kind of production primitives in that way, and it doesn't care whether the information comes from the auditory system or the visual system. Okay, so
a question here.
Yes. Okay.
How does, for instance, this explanation, say you're listening to somebody who has like a heavy accent,
Yes.
and you can't quite make out what they're saying.
Yes.
How does that factor into this type of explanation?
That's great. Yeah. So the module is going to be shaped especially by early experience. Okay. So the module is in some ways not just specific to speech, but it is specific to one's native language. Okay. What I mean by that is, so as we've discussed, I believe, we're born with a brain that's flexible for all languages. It can handle all languages. But in order to establish that efficiency that we're discussing, the module has, it has to narrow itself in terms of its segments, its processing to its native language over the course of a year and a half, right? So now, there's some great examples of this. There are languages, certainly, that have speech sounds that are not heard by us as speech sounds. So, OSA, you know that language? Sure. OSA. That's a language. It's African, I believe. And its first segment is, in fact, a click, OSA, right? And there's more than one type of click. I think there's 2 or 3 types of clicks. So OSA versus OSA, okay? And to us, since we didn't grow up with that language, those clicks kind of sound like, if you ever, there's a terrific singing group, Lady Black Mambaza, I think, if I'm pronouncing that right. You've heard it before, probably. And they do sing in that language, and you hear, as you're hearing them sing, you do hear kind of like these clicks that kind of rise above the singing and rise above the language that doesn't really sound like speech. And so the idea here is that because the speech module isn't tuned to those clicks as critical phonemes, in this case, it does sound like non-speech. That's a kind of intuitive example. But the ones, the segments in that language that are more like English for us, if we're native English speakers, or, if regardless of your native language, if those segments are in some way close, then they can be perceived as speech, but you might not be able to make the, kind of important discriminations that are necessary for you to understand that language. That doesn't mean it can't change, but, it takes a lot of work, especially after, we're 2, 3, 4 years old. So, as you know. Okay. Other questions? Yes.
Sorry, you said those like the important discriminations. Is that because the brain is having difficulty understanding how that person is articulating it, or is it also based on the sonic characteristics?
Perfect question. I love that question. And the answer would be both, but mostly because of the articulation. So one way you can make somebody more easily understand a segment distinction that is not part of their native language is that you teach them to produce it, right? And of course, this is something that you know when you're learning a second language, that there's a constant kind of kind of trading back and forth of, okay, let's make if we have trouble understanding this segment, let's try to produce it ourselves and try to get the nuances of the production, and that makes it easier to perceive. Yeah. So yes, for this theory, you're not familiar with the production, the subtleties of the production that is producing that segment that is foreign to us. Great question. Other questions at this point? It was radical at the time, meaning that, first of all, two aspects of this were radical. First was the idea that we always make use of the motor system when perceiving speech. And secondly, that speech perception worked in a different way than perception of all other sounds. Both of those characteristics were radical at the time. At least the former has become a more accepted sort of concept in the perception and cognition literature, which is the idea that, in fact, we do make use of the brain's tacit knowledge of motor behavior in perception. So it's really interesting because I was as an old guy, I actually got to see the evolution of this. So the father of the motor theory, his name's Al Liberman, wonderful guy. He was one of my graduate advisors back at Connecticut. And we used to argue about the motor theory all the time. And the motor theory is probably one of the most influential theories of speech, or at least it was, and then it stopped for a while. Now it's come back into fashion, as I said. But this was back in the 80s, 90s, and we used to argue about it, and he would say that we're going to find as we do more and more fMRI that the brain is involved, the motor system is involved in speech perception. I actually thought that was a very sensible thing. I just didn't think it was necessarily specific to speech. And so we wrote papers back and forth on this. I don't think I've assigned any of the papers that me and my colleagues wrote about this, but I assigned a couple of Liberman papers, or at least one Liberman paper. But as it turns out, ultimately, sadly, after he passed away at the age of 95 or something like that, the research is showing that, yeah, it seems like, in fact, there is more and more, as we do more and more research on the brain and speech perception, the motor areas do seem involved. Now, this is still a real controversial issue. And in fact, arguably, last time I looked, which was just a few years ago, this is the most tested question in speech neuroscience. Okay, that the question. So if you look at speech neuroscience to understand what part of the brain does what sort of function, and what is this function comprised of, one of the most tested questions is this one. How much is the motor system involved in speech perception? Okay, so yeah, as we'll be discussing soon, it really kind of provided the groundwork for this idea of motor, kind of motor tacit knowledge being the basis of all of perception and cognition, as we'll discuss soon. Okay. Well, let's talk about this. Let's talk about it first in the context of speech perception. And the idea in speech perception was that since probably 2004, I think after Al Liberman died, there was evidence that when one listens to speech, there is activity in the primary motor and premotor cortices. They after a while had the technology to start localizing it, and they found that, yeah, the segments, the location where different segments are represented for production in the primary motor and premotor areas are in fact activated when listening to those segments. Okay, so it is kind of a segment-specific sort of response in the motor cortices as we're passively listening to speech. Okay, which is exactly the sort of thing Al Lieberman would have said, yippee, you see, all those years I was right. The motor system is involved in speech perception. Okay, and we have other great technologies now, as you know, TMS, which can either kind of break the brain. Did we discuss transcranial magnetic stimulation in this class? God, I'm getting old. I can't remember what I taught in this class. Okay, I think we know a little bit about this transcranial, maybe not. But you folks probably know it from other classes. The idea is that this is this best thing since Betty White, right? That you can not only image the brain now, but you can temporarily and to some degree almost precisely lesion the brain weakly and very temporarily to start looking for potentially causal mechanisms in the brain to degree we can actually talk about those things. And this is the device right here. It looks like these Mickey Mouse ears. There's various ways of doing this, but this is kind of the strong version of it. And you can put it around various positions of the brain and turn it on for a brief second. Actually, it does two things. You can, depending on whether you got a big pulse or like little kind of weak pulses, you can either lesion the brain, or with weak pulses, which I don't think we're talking about today, you can actually prime the brain, which is interesting. We'll talk about the breaking of the brain stuff, okay, which is sometimes called the RTMS. If you, in fact, ask people to listen to speech passively, they're not speaking, they're being completely quiet, but they're listening to speech passively, as you apply this what's called RTMS to the motor cortex, I guess in this case it's premotor areas, it makes it somewhat harder for the people to understand what's being said. It makes it harder to identify speech syllables and noise. So just, what is that? Ba, da, ga, bi, di, ji, gi, all those sort of things with a background of noise, which makes it challenging. People are worse at that if you break temporarily the premotor cortex that's involved with the production of those syllables. Okay, this thing is precise enough. I don't need to pull up my brain hat, do I? Okay, this thing is precise enough that you're not actually affecting the auditory cortex or Wernicke's area or anything like that, right? You're affecting the speech motor system. In all intents and purposes, you're not affecting the typical recepting system, but instead the command issuing system, the motor system. But even doing that does seem to affect perception. And again, now as we've gotten better technologies, this is also shown to be segment specific. So you can just make it harder to perceive ba's against noise by kind of, very precisely going for the ba area of the premotor cortex. Okay. Again, it's not over auditory cortex. It should have nothing. You're perfectly fine at listening to all other sounds. It's over the motor cortex, suggesting that, okay, so maybe this motor theory has some validity to it. It is using this motor information during perception. And if the motor information is temporarily wiped out with TMS, it's not going to perceive as well. Okay, very cool. Okay, so if nothing else, what this might mean is that that when you ask people to classify phonemes, like in this task, where you're identifying phonemes against a background of noise, motor system involvement is something that we use. Okay, so the motor system, at least at that point, it is something we use. All right. So good for Al Lieberman, good for the motor theory of speech perception. However, the debates here are kind of fun, and I've been a little part of them with the new neuroscience. I think there's some interesting things that go on with multisensory speech, which we'll talk about later with regard to motor involvement. Just to anticipate, there is this absolutely, wrong theory that claims that in order for us to integrate the senses, we must make use of the motor system. And I think that's absolutely wrong. But let's go ahead and talk about the controversy just within auditory speech perception. So all of these TMS effects, and there's many more you can read about, all of these TMS effects do affect, so when it's TMS on the motor areas, they do affect perception, but a tiny bit. And here we're talking about 10%. It's consistent, right? I mean, it works with pretty much everybody who's been tested, but it's not like you can't perceive these segments. You can't perceive them quite as well as before. The degradations are subtle. Also, okay, your ability, the disadvantage that the TMS is giving you in these tests seem dependent on degraded stimuli. So you're now listening to the speech in the clear, what we call in the clear, with no background noise. Ba, da, ja, la, that sort of stuff. And you're getting TMS'd, bam, 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 in your motor areas that should be, according to the motor theory, related to speech perception. It doesn't work. I mean, what I mean by that is you're still able to perceive those segments perfectly fine. So the effects that we've been discussing, where TMS, the TMS application to the motor areas, only seem to affect perception with degraded stimuli and in a very, very low level way. Most of those segments you can perceive just fine. Okay, so you see where this is going now, right? That in fact, it could be that, yeah, maybe there's a little motor involvement, but maybe that motor involvement isn't necessary at all. Maybe, you know, when we're dealing with noisy speech, difficult speech, yeah, okay, motor system, come on out and help me. But for the most part, maybe it's not really needed because the TMS is affecting the motor cortex and it's not affecting the perception. The other alternative here, though, of course, and this is something we have to consider with TMS, is how much TMS is needed. Maybe the TMS is not completely deleting the motor system or the motor system that's involved. So, you know, when you TMS the premotor cortex, it is going to affect the way a person articulates their own speech to some degree. I mean, it's going to show, you know, differences in coordination. So, you know, that's how you're targeting the person's premotor cortex, okay? You know if they're having problems articulating, a little bit of a problem articulating, that, you know, that you've got the premotor cortex. But perhaps that TMS is just not strong enough to really wipe out what the perception system uses from the motor system. So how do you know if this is an issue of very little motor involvement in speech perception, or the technology's not quite doing what you're assuming it might be doing? Okay, and this is a really kind of difficult thing to determine in this literature right now. It's part of the debate that's going on. So what people do is they look to other sorts of evidence for this sort of thing, including looking at what we call Broca's aphasic. So these are people that have a motor system, a speech motor system problem because of a stroke, most usually, or it could be an accident, but it's most usually a stroke. Do Broca's aphasics, okay, have trouble perceiving speech? And as it turns out, they do, a little, okay? They can understand speech pretty well until you get them into a noisy condition. So into a noisy restaurant, you play them speech syllables again with a background of noise, right? And at this point, Broca's aphasics will say, yeah, I'm having trouble. Well, it's hard to understand them because they can't articulate, but they'll indicate they're having trouble perceiving the segments, perceiving the syllables, okay? So this is now without any TMS. This is kind of nature's TMS because of the stroke. It does affect their perception, which the motor theorists would predict, but it's just a little bit. So what do we make of this? Well, it could be that maybe we're talking about motor involvement for certain types of speech perception, but possibly not for everyday speech perception. So, I have not, I wrote a paper on this about 2 years ago, 2 or 3 years ago, and that's the last time I looked at this literature. I'm saying this because this literature is growing so quickly, I don't know where it stands, but the last time I looked at it, my interpretation was this, that there does seem to be motor involvement, but in limited circumstances. So when you're asking subjects to do what we call explicit phoneme classification, and it's basically just identifying the phonemes, identifying segments, identifying syllables, in an experiment. So you zap their premotor cortex, and you have the syllables with a noisy background, so degraded speech. Yeah, you might find that they're not as good as if you didn't zap their motor cortices, right? There's also, as I suggested before, that for multi-sensory speech, we might need motor involvement. And boy, this drives me nuts. And this is something this is one of my bugaboos. You know that term, bugaboo? We just had Halloween. I think it's a good Halloween term. But it really bothers me because I think there's absolutely no strong evidence for it. And I think it gets the whole idea of motor involvement completely wrong. But there is this group of folks that believe that we must use our motor system, our speech motor system, to integrate audiovisual speech. So, they show that the McGurk effect might not be as strong in people who have their motor cortex TMS'd. Okay, we'll talk about that later on. But the other thing is, all of these experiments where the motor system is TMS to show effects on perception, all of them involve some sort of immediate motor response right after they hear something. So this is not something that really affects like conversational speech. This is something where people hear it as they're being zapped and have to respond immediately to each syllable they hear, okay? Suggesting that perhaps our motor involvement in speech perception is really, for degraded speech conditions or, speech conditions where we're asked to do things we're not normally doing, okay? Suggesting possibly that it's not the normal circumstance, okay? However, other folks will come back and say, hey, listen, when do we ever hear speech that's not noisy in the real world, right? So in the laboratory, certainly, you can set it up to be quiet and with no background sound because you're wearing headphones and you're listening to completely clear speech. But my gosh, that is not how we perceive speech in the normal world. In the normal world, there's slips of articulation. There's always some background sound. So in this room, I'm hearing background sound now. You're probably hearing some background sound where you are. So speech really, functionally, people will argue, is always degraded. And so it needs that kind of motor system, kind of implicit knowledge, that NASA simulation in order to do this, in order to perceive speech. So the normal circumstances of speech require motor involvement, even if certain laboratory examples don't. And this is kind of where the debate has stood over the last, few years at least as of 2-3 years ago. This is where the debate is. My current feeling is that I think that motor involvement in speech is available. I think it's probably very much used as we're learning a language, including our first language. I think that probably motor involvement in learning distinctions for our first language is probably important. Motor involvement, both tacit and active, I would say, and learning a new language certainly. Is it required for normal speech perception? I don't think there's enough evidence to show that it absolutely is required. But that being said, there's a lot of folks that disagree with this. It's an open question, and it is the most tested question in speech neuroscience. Let me just say a tiny bit before I kind of conclude our discussion on modularity of speech. Why is this the most tested question in speech perception? I have a feeling I know why, and that is because I think it has implications, as we'll discuss in just a few minutes, for general perception and general cognition. Because there is, kind of a more modern school of thought suggesting that all of perception, all of cognition is tied to our body, is tied to the motor system, whether it's actually a true active body involvement or some sort of tacit body involvement in making use again of what the brain and body know of how behaviors are produced. We'll talk about this as we go through mirror neurons in just a second. But I think that it's a popular topic to study in speech perception because it's because of its implications beyond speech perception. Okay, and there's this large literature, showing potentially that speech perception is kind of the prototypic example of how motor involvement might be supported. So, think about some of these effects. The McGurk effect. Oh man, boy, does that show that the primitives are really amodal, right? The speech loudness focal effort effect. Oh man, does that show that we are really dealing with primitives that have to do with the articulation, not the superficial acoustics or something like that, right? So there's this huge literature that kind of supports behavioral literature that supports this involvement of production in perception, and that that kind of is another motivating factor for this being one of the most studied issues in perceptual neuroscience, I would say, not just speech neuroscience. Okay, all right. I'm just going to do a summary slide on modularity, but before I do, let me take a second here and see if people have questions about this. Nothing? You guys are still there, aren't you, boy? Sometimes I get talking and I forget that you're there.
Sorry, so do you have any examples of what degraded speech is?
Oh, I'm sorry. Yeah, what else I mean by degraded speech, it can be a number of things, but I think in a lot of these experiments, it's just speech against a noisy background. So you hear, syllables ba da, and there's a background of noise. Can you hear that okay?
Mm-hmm.
Like that. There's lots of other types of degraded speech. So the type of degraded speech we're working with in our lab now is called vocoded speech. And I won't get into the technical details. If you're interested, Mac, I know you're interested in sound and acoustics. I'd be happy to talk to you about that later. But the reason we use it is because it simulates, hopefully, what cochlear implant speech is like. I mean, it's the same type of technology that is used for cochlear implant signal. And it kind of sounds a little bit like Donald Duck speech. It sounds kind of like raspy speech. I have examples I'd be happy to play you. But I don't think many of these experiments use that. I think most of these experiments that test neurophysiology of motor involvement in speech actually use speech and noise, which is just white noise, a noticeable, pronounced white noise background against syllables. Okay, does that help?
Yeah.
All right. Other questions about this sort of thing? Okay, then let's just do a final conclusion slide on modularity. And maybe then we'll take our break a little early today because it's a nice place to take a break. So, is speech modular? Remember, this is kind of how we started the question. We got into speech, moved into motor involvement and the motor theory and all that sort of stuff. But the big question had to do with modularity. And that's, kind of modules are a form of computational sort of theories that are, kind of more specific, but it's still part of a generalized computational approach. Anyways, is speech modular? Well, let's discuss first of all the characteristics that we listed before, that modules are ecologically relevant, that they anatomically distinct, they have processes for which we don't really have much conscious awareness. Also, those processes are impenetrable by outside information. In other words, it's difficult for us to be able to kind of defeat the processing, the normal kind of workings of the module. And finally, the idea of all relevant information being available, whether it's coming through the eyes, the ears, or the skin. Oh, and of course, the functional relevance, which probably I should just list as another one, or I'm sorry, the functional distinctiveness, which I probably should list as another one, the Jerry Fodor, the modularity of mind paper lists these 5, so I'm kind of keeping with those. So let's go ahead and talk about each of these. Well, certainly speech has this tremendous ecological relevance. All cultures have a spoken language. Not all cultures have a written language, but certainly all cultures have a spoken language. We seem to show this predisposition where we can distinguish segments and kind of remarkably segments not just of our own native language, but segments of other languages, at least up until about a year and a half of age. Clearly, we have this specialized anatomy, which is going to be, kind of one of the motivating factors for modularity to begin with. So that, we knew this back then, that in the 80s, that there were various types of aphasia that seem to, be specific to specific areas of the brain. So, and the same thing with face perception. Remember, that's the other example that we're going to keep in mind with regard to modules. The processes seem mandatory in that there's not much we can do to not hear speech if there's a speech in the signal. Remember, this is the idea of this kind of preemptiveness process too, that not only is the speech module going to have processes that are automatic and are impervious to any sort of outside knowledge we can bring to bear, but also it seems to kind of be a little selfish and elbow out the rest of the brain and be the first thing to actually look at the acoustic signal and then pass that acoustic signal back to the rest of the brain if there is some sort of remainder left, as the turkey call sort of sounds I was discussing before. And of course, it's this prime example, and I think probably the McGurk effect is one of the reasons that the speech is still considered one of the kind of, I don't know, best ways of testing general questions in perception. There is no better multisensory, or I say no better, no more popular multisensory demonstration than the McGurk effect. And when we talk about that later on this quarter, I'll give you a little bit more history of the number of papers, the number of studies, and all that sort of stuff. But I mean, you want to test multisensory perception in general. One of the first places you look is the McGurk effect, even if you're not a speech laboratory, right? Because it seems like such a phenomenologically compelling demonstration, right? So yes, it is speech is supremely multimodal in that sense. So from everything we've discussed, it seems that speech is modular. It is kind of one of the prototypic examples of a module. And as we'll discuss later in the quarter, this is also true of face perception, right? Just to kind of anticipate where we're going with that one is that, face perception, has this tremendous ecological relevance. We get so much information from a face, not just, the ability to recognize our kin and our friends and stuff like that, but to recognize what those people and strangers intend towards us, right? What their emotional state is and how that can shape their intention to us, whether they're angry or, whether they're happy or that sort of thing. The anatomical distinctiveness of the face area we'll discuss later on. We see things, we see images having faces, even though there were no faces actually there. We can't help but see those things as faces, as cognitive impenetrability would suggest. And as we'll discuss, there's this, newish literature showing that whatever sorts of kind of functional distinctiveness seems to occur for face perception, not just applies to seeing faces, but also applies to touching faces, which is just fascinating. So the idea of all relevant information being available to the face module, like it seems to be available to the speech module, is pretty clear from the literature. Okay. Any questions now generally on modularity? Because we're going to leave this topic. I just want to kind of go back and just very briefly address this term modularity, because I am talking about a very specific type of modularity that was discussed mostly in the 80s and 90s. And when the term modular is used now, it doesn't necessarily depend on these characteristics as they're listed there. The problem is sometimes it does, but other times it doesn't. So sometimes this term is used very loosely. Sometimes it's used very precisely, like it's listed here. Other times it seems like, well, modules should be able to take in multisensory information, but there needs to be no evidence for anatomical distinctiveness, or just the opposite. Actually probably the opposite is more common, that, well, we see evidence that there's a part of the brain that's responsible for this, but it doesn't need to take in multisensory information. So, it's important you know the history of modularity in order to kind of see how the term has maybe become too loose in a way. Right, so when you'll see as you go through your lab's literature and all that, you'll see the term. Certainly, you'll see the term, regardless of whose lab you're in. But I want you to know that historically there are things that come along with it, and I want you to be able to look at the modern literature and say, okay, it looks like this author means this by it, this author means that by it. If they're arguing about whether something is modular or not, there should be some common ground. So if nothing else, you should understand that this is a very loaded term. That means loaded, that it's got a history to it, and it can mean different things to different people, such that the discussions, the debates can sometimes kind of miss each other a little bit. So if nothing else about modularity, I want you to be aware of that going into the more modern literature. That being said, each of these characteristics, ecological relevance, anatomical distinctiveness, all that stuff, on their own, even kind of extracted out of the modularity discussion, certainly bears strongly on the modern literature. Okay, are there any questions about modularity or anything we've been through with regard to speech or motor involvement or anything like that at this point?
If you had to list all of the modules that people have made like compelling theories about,
yes,
what would those be?
Okay. So in your paper, the Précises of Modularity of Mind, Fodor does do a little bit of that. He shows strong support, at the time at least, strong support for the speech module and the face module, but he also discusses things like possibly sound localization. And you know how sounds are localized using the information that comes to our two ears, such that a sound that's coming from over here reaches this ear sooner than this ear and reaches it with more acoustic intensity than this ear. And we know for certain that the brain can make use of that different information to the two ears to be able to determine where a sound is. What he'd say is the fact that you actually can't hear a time difference, but instead hear a location, suggests that might be module. Okay, so I'm not going to answer your question by saying these are absolutely modules, these are strong modules. I'm just trying to give you a sense of the sort of things that led people to consider these things modular. Okay, so without being able to cognitively penetrate this, without being able to understand that there's a time difference there, you have no sense consciously that you're really hearing a time difference or you're really hearing an intensity difference. You're hearing a location. And so what the speech module, the face module, and in theory, a sound localization module have in common is they are dealing with not the sensory dimensions, but the distal event properties, right? You're hearing not a time difference. You are not aware of that. You're not hearing the squawks and noises of speech. You're not aware of that. You're hearing a position, you're hearing a location of a sound source, and you're hearing for speech the articulation that's molding the sound. Okay, so I guess what Fodor would say, other people at that point would say, when you find strong evidence that the primitives, that what the brain is actually working with is a distal event property, something to do with the properties of what creates a sound, okay, what reflects light for faces, that sort of stuff. When you find evidence for that, then you're dealing with a module. Something else for sound localization. You probably know about the ventriloquist effect, right? So the fact that you can get a sound to seem like it's coming from another position by showing a ventriloquist dummy talking, right? So you know how a ventriloquist dummy works. I'm talking like this, but here's my dummy, and it sounds like it's coming from his voice. And this is how movie TV works, right? A lot of the sound from TV comes from speakers that are, especially in surround sound, from over here, but it looks like the sound's coming from where the mouth is talking. That visual capture is an example then of a kind of sensory integration, where we might have something like a location module that integrates visual information and acoustic information such that it's an amodal primitive. So when you find evidence for like that sort of amodality, when you find evidence for a lack of being able to really experience the sensory processes, then you're possibly talking about a module. The other things are, the color. I think I listed some of these before. Color. What else? There were a couple of other things I can't remember. But no, the strong ones, the ones they really, the research that was done to support modularity, most of it was done on faces, on speech, and I think to some degree sound localization. That's where most of the research went. And it wasn't, the idea was that they didn't want there to be a lot of modules. They just wanted there to be a kind of a handful of modules just for the most kind of important classes of stimuli, or the most important function, that most ecologically adaptive sort of things that we use to survive. And then they wanted the rest of the brain to be responsible for all the other stuff. Okay.
What about gustation, like smell and taste, kind of?
Yeah, it's a really interesting question. I don't remember the old modularity folks addressing that so much. That being said, there do seem to be some examples in, for example, taste, where it is so multisensory, right, that we experience taste where it's really smell that's being involved. 80%, they think 80% of our experience of flavor comes from smell. Boy, that seems modular in the sense that we don't have access to the sensory primitives. We don't, when we experience flavor, we experience it on our tongue. It has nothing to do with a smell, at least in terms of our phenomenology. So yeah, maybe. Yeah, it's a really good question. I can't remember what they say about it. It might be in that paper.
I was thinking too, like the texture of things kind of influences the taste of them. Like if it's a bad texture, you assume that it's bad.
Yeah, in fact, on what's today? Today's Tuesday. Yeah, so tonight I'm talking about taste in my other class tonight, and I'm talking about it as a kind of the most intersensory sense there is, where probably very little of our experience of flavor comes from the tongue itself. It comes from the taste buds themselves. It comes from the influences of tactile input, olfactory input, certainly. And then there's this great research showing that also visual input has a very strong influence on taste. And the example I give there, just as an aside, is the experience I had going to a dark restaurant, and there's one in LA if you're interested, where you go in and it's completely pitch black, and you eat your entire dinner without ever seeing the food and what that's like. And then there's this evidence too that the sound of the food makes as we're eating it has a bearing on flavor. So yes, absolutely correct. Taste is probably the single sense that's most influenced by the other senses, and it's dependent on the other senses to work. So I don't know. I mean, I'm not sure if people have thought of taste as being a kind of prime example of a classic module. It's a good question. Other questions? Okay, let's take a little break here, and then we'll come back and talk about motor involvement and perception and imitation and mirror neurons. Okay, see you in 10 minutes. Hello. How you folks been doing? Anyone been able to go to campus yet? No? Okay. I've been chatting with the faculty, and I think they're planning on, some of them are planning on opening up the labs for folks, but it's, you know, there's a lot of considerations, so I can understand. We had a discussion with the whatchamacallit, the subject pool, or the human subject pool board guy last faculty meeting, and they know how they're going to kind of proceed once we get kind of the county's okay to do things like, you know, bring in subjects or allow undergraduate research assistants to go to the lab and all that sort of thing. So, I mean, they've kind of worked out a very careful plan on how to make things more normal, but we have no idea when that will be. So, you know, it's unclear. But you know, at least you know, we know how it will happen if we don't know when it will happen. So we'll keep our fingers crossed. Pretty stressful day, I have to say. All right. I don't know if Michael's back, but that's okay. We're recording, so he can catch up if he wants. By the way, I wanted to mention, you folks don't have to show your video. I just need to know if you're there. So I'll assume, hey, Michael, you know, if during the lecture you don't want to show I'm not looking at your videos anyway. What I can see on my screen is just the slide and my image, because that's what I'm recording to YouTube. And then once somebody asks a question, then I look at you. But you know, it's completely up to you. Don't feel compelled. I don't know if other folks are making you show your video or not. I don't, you know, I don't care, whatever you guys are most comfortable doing. Okay, here's something that you'll be interested in knowing. When you teach a 3-hour class, whether it's an undergraduate or a graduate class, when you take a break, a 10-minute break in the middle of the class, it is the fastest 10 minutes of your life. It goes by so quickly. It's like, I'll use the restroom, I'll get a drink of water, and oh, time to go back. So here we are. Okay, no, I love talking about it. It's just starting. Lots of fun, tough stuff to talk about. Any questions before we continue our discussion? Okay, let me know. Let's talk about mirror neurons then, and a little background on this. This is still a fairly hot topic. It used to be a hotter topic. It used to be one of these things that in psychology, I imagine this happens in all sciences, but it certainly happens in psychology, when there's a kind of new major discovery where we have to kind of rethink aspects of the brain, aspects of behavior. People like to run with it and maybe take it to extremes that you know, kind of make folks rethink the entire idea. And that certainly happened with this mirror neuron story, and I'll discuss that a little bit. But I think there is an interesting story that is retained, even if it's not the, you know, best thing since Betty White again, that we did think it might be about 10 years ago. This used to be a really, really hot topic about 10 years ago, and I think it's a little less. It's become a little less central in modern neuroscience and modern cognitive and perceptual psychology. Although it still does have I think, play a role in other aspects of psychology, including in embodied cognition, as we had mentioned earlier, which we'll talk about later on in the quarter. But I kind of want to give a little bit about the history of this, and you know, maybe talk a little bit about the extremes that it's been taken to. But I also want to emphasize the thing I think is really important about this story, and I think it has to do with our understanding of how sensitive we are to other people's actions, which in some ways we've always known, but it could be that that sensitivity is based on the sort of thing to some degree that we are talking, that we discussed before, which is, kind of involving what the perceiving system, what the cognitive system knows about how actions are produced. Okay. So let's give the story. I guess this is true. I never, absolutely validated it, but I've heard it from more than one person. The way this thing was discovered, the way the mirror neuron system was discovered, was supposedly some folks in Italy doing research on motor behavior in monkeys and initiating motor behaviors, especially. We're recording from primary motor cortex, parietal and premotor cortex of the monkey as the monkey was reaching for raisins that were placed in front of it. I think they were doing direct cell recording with the monkey as it was doing this. So that's what you're seeing right here. The monkey reaches for the raisins, and those cells in parietal premotor cortex start firing off just like you would expect them to. Maybe they're discovering then something about the initiation of actions in that part of the brain. Okay, and then they give the monkey a little rest. The story is, you can use it, students like it. One of the grad students, I guess, because grad students aren't paid too much, right, got a little hungry and reached for a monkey raisin, him or herself. Okay. Now, I think you have to be pretty hungry to reach for a raisin that a monkey just ate, but still, or a monkey's had its paws on, but still, you do what you do. And so they reached for the raisin themselves as the monkey was resting. Okay. And the same cells in the premotor and parietal cortices started firing. So these are the cells I'm discussing as the monkey's reaching for it, and these are the cells that are firing, or this is the firing of the cells as the grad student is reaching for it. Okay? And what they ended up concluding is something really interesting. They test this again and again, and they test different groups of cells, and yes, they find this again and again, that cells that had been considered to be motor neurons, the cells that just were involved in initiation of acts and maybe coordination of acts, kind of higher up in the system, not individual muscles and things like that. We're not talking about those neurons, but neurons in the premotor and parietal cortices seem to have double duty. All right, so these are cells, cell groups in parietal and premotor cortex. They're not just active during the initiation of an action, but perception of that same action. Now, imagine kind of first discovering this, because back then it was really thought that there was a very clear division in, kind of the neural hardware that was involved in receiving input versus producing action, sensory versus motor neurons, all that sort of efferent, all that sort of stuff. But here's a group of cells that seem to have two jobs, double duty. They initiate actions, and they are also receptive to those same actions performed by somebody else. And in the monkey's case, it was either another monkey or a person. Okay. And so that's pretty profound. I mean, that really does kind of change our conception of how the neural machinery is kind of, divided up. We thought it was a very clear division, with some sort of, something in deep inside that kind of connected the input and the output, all that stuff. But now here's output neurons that also seem receptive to that same action performed by somebody else. And that, it's interesting. I mean, these neurons seem to have a little bit of a sophistication. Not only are they receptive to the input, they're receptive to kind of nuanced aspects of the input. Okay. So, for example, in these situations, I'm just going to talk about some of these. You can read some more about it. In these situations, okay, you see you see activation in those neurons, in those motor neurons, when there's an intent in the actual action. So here's a hand intending to pick up a box. If the hand goes through the exact same motion, but it's not clear what the intention is, right? There's no target here, then the cells don't fire. But it's interesting because this is kind of the sophistication of these cells. It goes beyond that. It doesn't actually have to see the contact with the little block here. What you can do is you can show the animal that there's a block there, or raisin, and then cover it up with a screen, and then show the hand going behind the screen, and it will set off those cells. But if, on the other hand, what it's showing down here is if you show that there's nothing there, right, and then cover it up with a screen, then it's unclear what the intention is, and therefore the cells will not be firing. So it's pretty remarkable, right? So not only are there motor cells receptive to perceptual input that are specific to the action, they seem specific to the intention of an action, right? It's not just the hand movement that's it's receptive to. It's that the hand movement is moving towards a target. That is very clear. That's when those cells go nuts. And I'm not going to talk about these there's other examples that kind of show this sort of thing, other very clever examples. But this was the first discovery, and you can imagine it was really exciting to think about that there were cells that had this double duty, that had a certain type of sophistication to them, and we never thought that those sort of motor neurons would work like that. So the name they gave these things, because they have both a motor function and a perceptual function for that same motor action, was mirror neurons. Okay, they were neurons that could act and then respond to kind of the mirror of that action in somebody else's behavior. Okay. So what are they for? What do they think they're for? And this is where we make contact with the motor theory. And this is, if you go through those early papers, they go right to the motor theory of speech perception. They go right to the Liberman stuff, modularity, all that. So it's, even though this is a very new concept, this is one of the lessons, the historical lessons that's really helpful here that they kind of use. Is say, well, we kind of know something else where there's kind of a system, in this case, I guess it would be a module, where it's responsible for action, speech production, but also it makes use of that information for perception. So the idea that a motor component could be used for perceptual purposes, its most, kind of fleshed out version was in the motor theory of speech perception. Okay. So the same idea. These are action simulators potentially. So the goal of these neural systems is to be able to perceive efficiently and accurately and in somewhat of a sophisticated way how to interpret the actions of others. Okay, how to interpret the actions of others. And so clearly this is connected to the motor theory. I mean, but now it's almost as if you're seeing the motor theory module in a group of neurons that act as both receivers and producers, right? So now, wow, this concept of making use of production for purposes of perception is not just something true about speech. It's something that might be true of the entire perceptual system and the motor system, and it might actually be instantiated in individual cells. Okay, so you can see how excited this is. And sadly, this happened very soon after Al Liberman passed away, but certainly his followers embraced this immediately. Some other things about these things. So they were certainly reactive. If you look at the relative activation, they were very active when a motor command is issued. They're active when that same action is performed by somebody else and you're perceiving it, not quite as active as the motor command. But they are most active. You see most of their activity occur during imitation. In other words, you train the monkey to, let's, kind of together, monkey see, monkey do. I'll grab some raisins, monkey, you grab some raisins, and that's where you see these cells go, yahoo, yahoo, isn't this fun? They are most active during imitation, okay? And in fact, okay, we've kind of localized these cells. This was a great time over the last decade went on, where we can actually now start looking at their causal involvement potentially, and so they TMS it. And what you find is that you make it hard for an animal to imitate if, in fact, you briefly, disrupt the mirror neuron system or these cells in a monkey with TMS. Now, I should mention what MNS, what TMS is. That's transcranial magnetic stimulation. That's the mouse ears that temporarily break a brain area. But I'm sorry, I don't know if you can hear this. My gardener's here again, of course, because today's class time. It's very distracting, but I'll get through this. What an MNS is mirror neuron system. Okay, and the reason we use that term for humans is because of the difficulties of doing single cell recording. So they discuss often mirror neurons for animals because these neurons have actually been identified with single cell recording. There is some single cell recording with humans, but I think at this point they still leave it as a mirror neuron system, and it's considered to be like a cluster of cells in the motor cortex, premotor cortex. Okay, so whether doing this with animals or doing it with people, if you TMS that part of motor cortex, you do show that people are inhibited in their imitation. And then there's tons of experiments, behavioral experiments, that show that imitation of an action actually facilitates that action. And some of these are kind of quaint, some of these are clever, but I'll just go through some of these now. If you're asked to press one of two keys and you're told which key to press, either by a dot being placed above the key or a photograph of somebody pressing the key, you're faster at pressing the key with a photograph of somebody else pressing the key. There's just tons of stuff where it seems that being able to get information about somebody else's action primes your own action. Okay, so let's talk first about the importance of imitation. And I think here, for me, this is some of the most interesting aspects of the whole mirror neuron story. I think that one thing we have learned almost as a byproduct of the mirror neuron story is the fact that we are consummate imitators. We imitate all the time, and our imitation facilitates our social behaviors, but also our cognitive and perceptual behaviors. That imitation, kind of like tacit imitation that we do internally, allows us to perceive each other better on a fundamental level. Okay? So the degree to which true mirror neurons are involved with this is a little unclear, but I think the insights it has given us about tacit and explicit imitation have been really important for the field. Okay? So let's talk about imitation. So first is explicit imitation. And clearly, we're aware of imitating for skill acquisition, right? Whether, it's imitating somebody else as we're learning how to dance. That's a picture from Dancing with the Stars, I think. Or learning language. A lot of what we do is explicit imitation of other people's behavior, and it allows us to acquire skills that way, right? But then it's thought that there's this whole other kind of category of imitation that we do that is implicit, and we aren't necessarily aware of doing it. Sometimes we can be made aware of doing it, but and I'll talk about some of those examples. But as I'll be describing them, most of them are, probably occurring at a level below consciousness, and for good reason. You wouldn't want to that to take up your conscious awareness, on a moment-to-moment basis. But what this implicit imitation will do, I'll argue today, is, as I said, it facilitates our perception. It allows us to be better perceivers. It allows us potentially to understand actions and the intent behind the actions better. It potentially acts as kind of a socio-emotional glue. And you'll see there's some ramifications of implicit imitation, unintentional imitation, inadvertent imitation, that affects the success of our social interactions. And, I'll just mention this a little bit. What's called other minds, kind of being aware of someone else's intent, someone else's emotional state, and how that might bear on intent. It's kind of a concept that's discussed very often in development when children kind of become aware that other people have intents and can have the intent to deceive. And often it's discussed with regard to various kind of social challenges, like an individual who has Asperger's or autism is sometimes thought to not have the same degree of insight into other people's intents, other people's emotional state, other people's kind of whole mind, I guess, behind their actions. That's not well said, but you get the idea. So mirror neurons were first kind of thought to be involved in all these sorts of things. And I'm going to say, I think, even if we're not going to come down solidly on how important the mirror neurons are themselves, I think there's an argument to be made for implicit or inadvertent imitation being more important than we used to think before the mirror neuron story emerged. Okay. I'm going to get, we're going to have a little fun here in doing this. And before we do this, I thought this would be kind of a nice tiny little break. What am I going to show you? Let me see, do I have this? Yes. I'm going to show you a cartoon from the New Yorker. Okay, so if you know anything about the New Yorker cartoons, they're subtle, but I want you to be honest. I won't be hurt as I show you this cartoon, because I'm going to have you judge how amused you are. However, I'm going to have you do different things depending on who you are. So it's kind of goofy, but it'll be fun. If Hunter and do you guys have like a pen or a pencil nearby? Do you have something? Okay. Yeah. Hunter and Mac, can you take your pencil and hold it in your teeth? Actually, you know, it'd be better if you do this. So it's sticking out. Okay? And then if we could have Michael and Morgan, do you both have a pencil? Put it in your lips. So do the same thing they're doing, but hold it with your lips, not your teeth. Okay? And now, here comes the fun part. I just want you to write this down or put it on your computer somewhere. I want you to tell me on a scale from 1 to 9 whether you find this cartoon amusing or not. And you can be honest, it won't hurt my feelings. Okay, write it down. How amused are you by this cartoon? Okay, great. We're going to come back to that later. But I'll tell you the correct answer, by the way, is 9. You should have been very amused by that cartoon. You can take your pencil out. We'll come back to that in just a second. I just want to see if it works. Typically works in a larger class, but we'll see. Anyway, do you get it? Robot pack. See, since cats don't do anything anyway, they that's how they pass the Turing test. All right. How many jokes do you find that relevant to this class? Okay. Let's go ahead and talk about this. And actually, we're going to come back to this in just a second. But what we're talking about here has to do with faces, obviously, as we'll discuss in just a second. But I think this is actually one of the most interesting domains in which we can discuss inadvertent imitation. So we're kind of moving away a little bit from a direct discussion of mirror neurons, and we're talking about imitation, which might or might not have involvement of these mirror neuron systems. Okay, so I'm just going to talk about the behavioral and some of the neurophysiological evidence that imitation turns out to be something that's very important. Okay. So we're talking mostly about inadvertent imitation. So, just to make this intuitive for you, inadvertent imitation involves like when you're talking with somebody and maybe you find yourself, speaking more quickly if they're fast talkers, or slowly if they're a slower talker. The one that always kind of embarrasses me is when I'm talking with somebody with a thick accent and I imitate their accent by mistake, and I always get embarrassed. As it turns out, actually, we're just starting a research project in my laboratory to see if, in fact, the person who was imitated, the person with the accent, is aware that they've been imitated, because we think that they're not. Okay, we think that other people might be aware, but if it's your accent, we think that very often they're not aware of somebody imitating the accent. But we can talk about that later outside of class.
Sorry, I was just a comment. I was going to say I have a friend who has this kind of a Southern African-American type accent, and when I'm talking to her, sometimes I say things like y'all and other thing, and I get like, oh God, what am I doing? And I don't know.
Do you think she's aware of it?
She's made fun of me for it a couple times, so I think probably. But
it's interesting if if it's recurring and you're using a different word like y'all. I wouldn't be surprised if she was aware of it, but I would be surprised if she was aware of kind of the more nuanced examples of that you're producing. So even though you might be aware of maybe having that kind of Texas thing, she might not be aware of it most of the time. I'm very interested in that type of question recently. Anyway, but we know this happens. We know that we do this. So these are examples where you're kind of you're inadvertent, you're accidental, you're unconscious, typically unconscious sort of imitation kind of emerges into consciousness for a second, and you realize, oh my gosh, I'm standing with the same body language as the person I'm talking to, or speaking faster, slower, speaking with an accent. And then sometimes we are aware of the fact that you might smile more with somebody who's smiling more, or if somebody's smiling less. Very often, different cultures have different, I guess, extents of expression. You might know a little bit about this literature, where, for whatever reason, in city centers, people, yes, they smile, they frown, but their smiles tend to be a little bit more constrained. Where if you go out into the countryside, the rural parts of outside the city, people's expressions seem to be a little bit more extensive. They seem to be a little bit more exaggerated, and typically people will, kind of match the extent of an expression depending on the expression culture around them, which is kind of fun. It's kind of all the social psychology stuff, but it's fun. Okay, but here's a cool thing. In the laboratory, if you ask people to, say, look at a series of faces that are coming on the screen and do something that's kind of a cover story, you're asked to press a button whenever you see an older face or whenever you see a face of a different gender, which you can do easily. But that's not really the purpose of the experiment. That's kind of a distractor story, so you're not aware of what's going on. What's going on is some of these faces are smiling that you're seeing, and some of them are frowning. And there is a camera looking at your face, as there is right now from my computer looking at my face, that's actually looking at how my face responds to the faces I'm seeing. And there's another thing. My facial muscles are being recorded with little surface electrodes, those little kind of pieces of little wires that are kind of taped to, over the muscles of my face in specific regions. And as I'm looking at these faces, if they are in fact smiling faces, even though I'm doing something completely different, consciously, I'm looking for older faces, I'm looking for different gendered faces, I will show face smile muscles activating. Okay, and sometimes it can be seen, like in these cases, it looks like it can be seen, by looking at the face. There's a person that's looking at a bunch of smiling faces. There's a person, that same person later on is looking at a bunch of frowning faces. And again, this expression imitation has nothing to do with the purpose of the experiment, as far as they know. Same thing here, smiling face. You can also measure this in the brows, I guess, but this is maybe where it's most conspicuous. It works, and it works whether or not. Sometimes it's visible. Sometimes, yes, the camera can pick it up, and people, naive people to the experiment will push a button and say that's a smile, that's a subtle smile, that's not a smile, that sort of thing. Or if not, it can certainly be shown with this kind of recording of muscular activity. It's electromyographic EMG. It just stands for muscle recording, and it absolutely works. So, the idea of a smile being contagious, it kind of is. I mean, at an kind of an inadvertent level, which is interesting. Yeah, certainly, it's one of the things I really miss about, seeing people's full faces is going to the grocery store and smiling at people. It's kind of makes me kind of feel good to do that, and makes me feel good when people smile back. And when you get older, those are kind of the kind of really mundane things that end up making you happier than you realize. But you can't do that now, right? And people are try to smile with your eyes and stuff, it's only so good. But you're aware of those instances. But the truth is, even when you're not aware of how a smile affects you, there is kind of this inadvertent imitation that occurs with the smile muscles. And it's pretty consistent. It can be very subtle, but it is pretty consistent. And this is just amazing. This really surprised me, is that you don't even need to know you're looking at a face for this to occur. What I mean by that is you could be in a completely different experiment in the sense of what you as the subject are aware of. I'm trying to remember the sort of cover story. I think what they do is they ask people to judge the beauty of different sorts of shapes or something like that. And that's your job, is just to look at the shapes, and on a scale from 1 to 5, how pretty is that shape or something like that. But what happens before the shape comes up is that there's a very quick flash on the screen that maybe you'll notice, maybe you won't, but you won't notice anything else. But what it is a face that's being shown to you so quickly that it's at a subliminal level, just meaning that it's below the level of your consciousness. It comes up and you don't see it. If anything, you just maybe see a flash on the computer. If you don't see, more likely you see nothing at all. You just think you're judging these shapes. But when that subliminally presented face comes up with an expression, you still imitate the expression, which I think is interesting. I think it's kind of cool that you can do it this way, but I think it really kind of speaks to kind of the power of this sort of thing, that it's affecting you at a level below consciousness so quickly that you can't help but show this little kind of muscular constriction that imitates either a smile or something more like a frown, which is pretty cool. What else? Well, what's the purpose of this? In the grocery store, it's nice. It makes us feel part of the community, all that sort of stuff. When we're doing it much more overtly, it's not the inadvertent type, really. But the inadvertent type might actually be involved with certain things. So it might help us recognize faces and their expressions. I'm sorry, let me say that again. It might help us recognize facial expressions. So what am I talking about here? Well, I guess I could talk about faces that are kind of like this. Now imagine these are not the subject faces here. These are actually the stimulus faces. And these are subtle expressions, right? So is this a smile or frown? Is this a smile or frown? And, it's difficult. It is challenging. But say you were shown a whole bunch of these things, and then you were asked maybe to look at faces that were kind of generated on a continuum. So you have someone smiling like this, and then someone frowning, and then in between you use Photoshop to kind of interpolate. So, you go from a very smiley face to a very frowny face of a picture of somebody. It's a photograph. But in the middle here, you have something in between. And those in between are going to be hard to categorize, and they're also going to maybe be hard to discriminate. Like if I showed you two next to each other in the middle, you might have a hard time determining whether they were different or not. Now, it would be challenging, but if your face was free to do that inadvertent imitation that you're not even aware of, you'll do okay. If, on the other hand, okay, your face is constrained in some way, and it can be constrained in a lot of ways. You can be constrained by having the motor area that kind of controls the facial muscles TMS'd, okay, broken for a short time. It can be constrained by you putting a stick in your mouth, like that. Okay, oops. And Botox, which I'll just talk about in a second. No, let me talk about it now. This is a replicated experiment. It's real. You know what Botox is. What Botox does is it gets, in theory, it gets rid of the wrinkles of your face by actually temporarily, I guess, inhibiting the inhibiting the muscles behind those wrinkles. So your crow's feet here can be less pronounced if you get Botox injections here, where the muscles that are involved in squinting your eyes, so the crow's feet appear, are, I guess, paralyzed. Is that right? It's some sort of poison that does something. I guess it paralyzes it for temporarily, so that when you smile, you get less crow's feet here, you get less wrinkles here, all that sort of stuff. I live in LA. I have friends that get Botox regularly, and if it's done well, you can barely notice it. Fine. Okay, so it does affect a person's own facial expressions when they are smiling and frowning. But here's a really cool finding. If those people are asked to make very fine-grained discriminations or identifications of expressions, they have more difficulty. Just like if their TMS has been, their TMS application has broken their motor cortex for a second, or they're holding sticks in their mouth, Botox affects one's ability to effectively do the inadvertent imitation of expression, and that bears on how sensitive a person's perception of another person's expression is. These are subtle effects. Let me be very clear. In fact, when I read this literature, that came out about 5 years ago or something like that, I went out to dinner sometime later that week with one of my friends, my wife's friend, who, lovely woman, I'm not judging, uses Botox, and I told her about this. And so she thought it was fascinating. And I said, okay, so let's test you. And I'm going to make expressions. You tell me if I'm happy or sad. And we had a great time with it. And clearly, she can read normal expressions, but subtle expressions like this sort of thing, she would be better at before she had her Botox injections than after. So the fact that the effect on her own muscles affected how she perceived other people's facial expressions is really, really interesting. Okay. I'm going to skip this next point. I think I don't really care about you knowing this. Yeah. Okay. I'll just say, these. How can I say this? Now, let me just keep that off. Okay, don't work with it interacts with emotion. What I do want to talk about a little bit is, where is this? Yeah, let me skip that. I do want to talk about this. And this is going to now go back, of course, to our cartoon. How our own facial musculature might affect our emotion. And what you just experienced in that little demonstration before was probably a much funnier cartoon when it was done, for the real research, was an effect that shows that depending on if your face is kind of structured, potentially unconsciously, to look, to be in the formation of a smile versus the formation of a frown, people find the cartoon more or less funny. So let's see. Let's pull you all back up here and let's see if this worked just for fun. Hunter and Mac, who had the pencil in their teeth. How funny did you find that cartoon?
Rated a 7.
Mac?
3.
Okay, you see, Mac, no, I won't take it personally. Michael and Morgan, who had the pencil in their lips. How funny did you find that cartoon?
I said 4.
I said 5.
Okay, so I think it might have worked. Thank you, Hunter. Hunter was just lying to make me feel better. Thank you.
No, it's because I have cats.
Okay, there you go. But you do this right. It seems to work. You put the pencil in the teeth versus the pencil in the lips. It seems to work. It seems to have some bearing. Now, I am going to be very careful here, because even though that was a fun little demonstration that I used to do in my large classes all the time, and it would typically work out okay, you'd be surprised, I have to be very careful here, and that's why there's an asterisk. So you folks are a great group to talk about this with, because I assume that at least most of you were at the cognitive lunch last week where we were talking about the replication problem, right? And that there was a large group of studies that were not being replicated that were kind of seminal in their fields. And this is one of those studies that was a very, very important finding that had a lot of influence over the field that has not been clearly replicated. So that asterisk has to do with the replication crisis. I have not kept up with this literature. This is kind of outside my own area of research. So I don't know where it stands now. You know, the replication crisis, you can imagine, my gosh, if someone tries to replicate your experiment and is unable to do it, you're going to run back in the lab and, you know, try to do it again and all this sort of stuff. And so all the papers that were criticized during the replication crisis have gone back and forth. Okay, so I don't know where it stands now, to be completely fair to the author, who I believe you're seeing the picture of right there for the demonstration. So yes, if you have a pencil in your teeth versus a pencil in your lips, it does seem to have some effect on emotion. And it's showed that it could have an effect on how quickly you can recognize emotion-related words. And so if you have the pencil in your teeth and you're in a, you know, word, non-word sort of experiment, press this button if you see a word, this button if you see a non-word, a nonsense word, you're faster at recognizing the words as words if they are related to positive emotions, like words like happy, positive, fun, those sort of words. You're better at recognizing those words, faster at recognizing those words, if the pen is in your teeth. If it's in your lips and your face is structured as a frowny face, you're better at recognizing negative emotion words, okay, like sad and disappointed, things like that, okay? So there you go. Now, importantly, it's got to be one of those experiments where, you know, there's a cover story about why the pen is in your teeth versus lips, and you probably figured it out when I asked you to do this. But in the experiment, typically the cover story works, and I'll tell you why I know that in just a second. You put a pen, a real pen, or some sort of stylus in their teeth, and every once in a while in the experiment, you have them actually type or try to hit a key on a keyboard. And what you say is that we're testing out ways of how people might react if they are paraplegic or something like that. Can they control a stylus well enough to make judgments on things, like stuff like that? So there's some cover story. And yeah, it does show, even though people at the end are interviewed and they say, yeah, I didn't know why I thought the pen was in my teeth and lips because you wanted me to see if I could control a pen for paraplegics or whatever, which is perfectly fine. What else? Well, you put a pen in somebody's teeth and they show an emotional reaction associated with, I guess, positive emotion, and including heart rate and galvanic skin response, sweat, that is indicative of happy emotions, versus if you put it in their lips, they show a reactivity in their physiology that is more indicative of negative emotion. Okay, this is the stuff that this research domain seemed to show, that by putting people in a a facial structure, a facial configuration that they were unaware was associated with emotions, it would still have a bearing on those emotions. Okay. Okay. The reason I say I have a little experience with this is I had somebody years ago in a undergraduate seminar that was really interested in this do something kind of cool. They were into industrial organizational psychology, and they knew that happy workers are more productive, right? Happy workers are more productive. So they wanted to see if doing this and having a cover story would have any bearing on productivity. And their productivity here was just measured by something very similar. It was long division tasks and I guess connect the dot tasks or something like that. But the cover story was, we want you to hold this probe, and every once in a while we're going to have you push a key so we can, see how coordinated people can be holding a pen in their teeth versus their lips. And yeah, he showed it. He showed that if it's in your teeth, you're better at long division, you're better at connecting the dots than if it's in your lips. Okay, we realized we had to do one more control because maybe it's harder to hold a pen in your lips than in your teeth. And I think it probably is. I don't know for those, Morgan and Michael, if you find it's not particularly comfortable and you couldn't do it for that long. So the other control we did is we put it in somebody's hand. And the prediction would be that's the easiest possible thing to do. It's much easier to hold a pen in your hand while you're doing these tasks than to hold it either in your teeth or in your lips. And what we found was that people who had the pen in their teeth were still more productive than those that had it in their hand. And the people that had it in their lips were still less productive than the people that had it in their hand. Okay, we tried to replicate it. It didn't come out cleanly. I don't know what to make of it, but I just thought I would mention this. I don't know where it stands right now, but I thought, I was going to throw it out this morning. I thought, I can't be absolutely convinced that where this is. I didn't look back at the literature to see where it's going, but at the very least, especially since we talked about this last week, I thought I would bring it in as an example of, one of the kind of, important studies that didn't at least initially show a replication. I don't know if it ultimately did or not. Okay. Last thing I want to say about this, though, very quickly before we leave the face stuff is, let me just say this, that the explanations these folks give for this is that emotions are actually really embodied, that this goes beyond the course. I don't know very much about, theories of emotion or research on emotion, but there are theories that suggest that you cannot ever separate one's emotional life with their physical life, in the sense that even subtle things that the body is doing will have an effect on one's current emotional state. And so in this case, placing the face in one configuration versus another should clearly have an effect on emotion, because these are emotions are from the body, whether it's including the brain, but also the kind of the gross anatomy of the muscles and all that sort of stuff that are involved. Okay. One more thing I wanted to say about this, just for your own interest, I think there is research on spousal facial convergence. The longer people are together, especially if they have an empathetic relationship, the more they grow to look like each other. There is no evidence that occurs for doggies in people. I know that's what you're thinking, but it does occur for people. So the idea of people's kind of facial structure changing over many years, as the wrinkles come in and the facial muscles get exercised in one way or another, shows kind of the importance of imitation in that type of thing. So anyway, just as an aside. Okay, let's continue talking about this a little bit and talk about the social aspects of imitation. I'm going to move through this a little bit more quickly, but I think it's very easy to understand. So what we're talking about here is the imitation that we do with each other when it comes to things like body language. And you're probably aware, as I said, you probably have caught yourself, at a party talking to somebody, and you then realize you're both crossing your arms, or you both have your hands on your hips. I think it's a kind of very common occurrence. And these sometimes are called chameleon effects, as chameleons kind of, change their color depending on their context. The idea is that we change our kind of, our physical state, or, our macroscopic physical state, where our limbs are, depending on our context as well, and depending on who we're talking with. And we know from the social psychological research that we copy each other's postures and mannerisms and speech, which we will talk about in some detail in just a second, to a measurable degree, certainly. And what we know from these experiments is that it has a bearing on social, I guess, success, people's impressions of others socially. And there's been a lot of experiments that have tested this sort of thing. And these sort of things have absolutely been replicated. We're not talking, even though it's more in the social psychological domain, it's pretty solid stuff. What you're seeing here in that little image is kind of what's called a Confederate experiment, in that two subjects, wait outside the laboratory to come in and participate in the experiment, and they chat about which intro psychology their course they're in, and how they like the teacher and stuff like that. And then they come in, and they are asked to describe pictures to each other. I think that's what they're doing there, so that the other person could potentially draw that picture later on if they had to. So there's Alan Alda, if you're interested, an actor that's part of a Scientific American series. He's saying, okay, I see there's a street scene, and there's an ice cream truck, and I see there's people walking down the street, and the other person's listening as he's describing it. Okay. Now, unbeknownst to him, the other subject is not a subject. They are, in fact, a confederate, which just means they're part of the experiment, right? You've probably heard that term. They are an experimenter that's posing as a subject, because they want to be kind of a secret experimenter that can actually induce the manipulation, kind of create the manipulation here. So after he is done describing, she'll start describing her pictures for ostensibly the same purpose, so he can draw the picture later on. Okay, I see a beach scene, and people are carrying surfboards. There's somebody sunning themselves on a towel, on and on. And what she's going to do is imitate subtly the sort of mannerisms that he performed. Okay. And then at the end, some really interesting things happen at the end. They're asked various questions. I mean, I guess after they go through this interaction, they're separated and say, okay, you come into this room now, you stay in this room. And then they'll ask the real subject questions, like how successful they think the interaction went, how likable the person was, various things like that. And if in fact the person was imitated in this in a subtle way, they will report things like, oh, I think it was a successful interaction. Yeah, I thought she was very nice. I really liked her. And it goes on and on from there. Being subtly imitated has a bearing on one's impression of the success, and potentially, to some degree, the actual success of an interaction. Okay, so the Confederate design of this experiment allows them to test this sort of thing. But it's been tested in other contexts too. Waitresses that do a little of this, they're trained in doing this for the purpose of the experiment. One's opinion of a product that a person is selling, or sampling in a store. If that person does this kind of subtle imitation, it works. Avatars, don't worry about it. It's a long time to explain. It just has to do with computer imitation, getting a voice to imitate the voice of the user and all that sort of stuff. But this imitation does seem to facilitate the social connection between the people. The imitation has to be subtle. It has to be delayed. So it is absolutely not the imitation your annoying little siblings used to do of you when you were growing up, Right? My kids did this, I noticed between them, and I certainly did this with my little brother. You know, you imitate them and say exactly what they just said right after they say it. Oh my gosh, it drives you crazy as a kid and it drives you crazy as a parent. That's not going to facilitate a positive interaction. It has to be subtle. Okay, so if the subject is doing a lot of this, then the confederate is going to do this maybe a little bit more gently, and it's going to be a little delayed. It can't be right when that person is doing it. It can't be conspicuous. It has to go under the radar, so to speak, right? But it goes beyond that. So it's really interesting. Say after, we'll go back to our experiment and we've just interviewed the guy now, the real subject now, and found out what he thought of the interaction, what he thought of the person. They say, okay, I'll be right back. I'm going to go get your credit receipt, and then we'll be finished with the experiment. And as you come back so you leave the room, and then you come back with not just the receipt, but a whole big stack of papers with 10 pencils. I wonder if they still do it this way, but 10 pencils on the top of on the stack of papers. And you walk in, and then you accidentally kind of trip, and the pencils go flying. Okay, this is actually a manipulation. The question is, does this real subject help you pick up the pencils? And they would be more likely to if, in fact, they had just been imitated, okay, inadvertently imitated. So it generalizes. This kind of social facilitation generalizes beyond the mimic and makes somebody more altruistic. And that has been replicated not just with pencils, it's been replicated with I guess you then are given a chance to donate your $5 that you've gotten from your participation to some cause that's, there's a little bucket on the table, and it says, please consider donating your subject money or some of your subject money to the homeless or something like that. You'll be more likely to do that, be more likely to donate if in fact you had just been imitated. So it's a pretty strong effect. Okay, I know I'm going through this kind of fast, but I think it's fairly easy for us to kind of conceive of. It's interesting. Yeah, I just read a little bit about this. Let me skip this, actually. Let me skip this, these details. It's a long story. I don't care you really know about this. This is really much more hardcore social psychology. But what I do want to talk about, and oh boy, I wish I had an example of this. I do have an example of this. Okay, there's a video that I just tested during the break and it did not work, so I'm going to do it for you. And this is the psychology of magic. And what you would see, I'm going to see if I can show this to you. What you would see in this video is somebody throwing up a ball like this, okay? Just like that. Okay, here we go. 1, 2. Okay. Oh, I didn't do a good job, but there you go. Thank you very much. What you would see is him throwing a ball 3 times in a row, and then the last time the ball seems to disappear. Okay. However, if you notice the way I did it, the last throw, I didn't throw it up, but my eyes went up. Okay. And what you find is that people are tricked more. They don't know how the trick was done if that happened. If, on the other hand, I did it like this. 1, 2, oh shoot, let me do it again. I tricked myself. 1, 2, 3. If I did it like that and looked at my hand, it would not be an effective trick. And the point of that is that when you're doing something like a magic trick, or any sort of, this is done in sports. I was just watching football this weekend, and the kind of misdirection that's done in magic is also done with football. You pretend to hand the football off to the running back, and then you actually keep it here, but your eyes can stay on the running back. A quarterback eyes can look this way, so the defense thinks that they're going to pass there, but then they pass this way. It can be very effective. I can say that the ball's in this hand, but it's actually not. What happens is your awareness, oops, let me go back to here. Your awareness is going to depend on where my eyes look. And this is one of the kind of most powerful tools of a sleight of hand magician, that they are going to look to the fake past hand, okay, point to it maybe and all that sort of thing. And even if your eyes don't go there, your awareness kind of does. And so it's a really kind of great example, and it's kind of a fun example because it's in magic, it's in sports, it's all over the place, of kind of how one's attention can't but help be influenced by imitating somebody else's attention. And there's a really long literature on this. And a lot of this literature has to do here, like I think I have pictures of faces here. Yeah, showing photographs or showing videos of people looking in different directions and how that facilitates or inhibits one's own kind of reactions to the things they are or not looking at. And again, it's one of these great face experiments. So a lot of these face demonstrations work with subliminally presented faces. So you don't even need to know you're seeing a face of somebody looking in a particular direction like this. Okay? That facilitates your reactions to this side of the screen, but not that side of the screen. It works even if you don't know you're seeing a face. You just see a flash on the screen or something like that. Okay. Again, it's like that last experiment with the subtle smiles and all that stuff, or the smiling folks that induce subtle smiles. You don't even need to know you're looking at a face for this to have an effect on kind of your natural imitative tendencies. Okay, so this kind of this natural, this way of our brains kind of always imitating each other works at a very fundamental level. Motor priming, which direction you're looking at. All this sort of stuff. This is just some of the stuff that has been tested in these experiments. You find products and more or less appealing if people look at it. Again, with subliminal faces, it still works. If someone is shown with their eye gaze looking at a product, you find that product more appealing, which is something they know in advertising, of course. But the fact that it works even with subliminal faces is pretty powerful. You don't even need to know you're looking at a face. The effect, we're not talking about subliminal advertising in the sense that people are going to go out and buy a product that they didn't want to. These subliminal effects are subtle, but they still seem to tap into some imitative tendency. In this case, imitation of attention. We are very, very aware of other people's attention, and it affects our own attention even at the subliminal level. So it's another type of imitation that occurs. Okay, let me continue with this. I know I'm going fast. Yes, go ahead.
One little comment again. I was reading an article about how people are viewed as like less trustworthy and friendly over Zoom.
Yeah,
they found out partially it's because like a lot of times people don't look straight into the camera when they talk. Yeah. They look at something else going on the screen, or they look at someone else's image, which is usually up in the left corner or something like that.
Is that something they actually examined empirically, or is that the kind of interpretation without kind of confirming?
I think it was in like from like a business context, so I doubt it really had major empirical support. But
yeah, well, you can't see my screen right now, but next to where my camera is on the screen, I have a little smiley face sticker to remind me to look into the camera, because I know it does make a difference. I mean, people think they're being polite by kind of looking down here as they're watching you talk, and then they talk back to you, and I think people's reflexes are to look at the image as they're talking, but it is a little off-putting. I think everyone understands it, what's going on and all that sort of stuff, and no one takes it consciously personally. But yeah, I could imagine that absolutely is something that would happen. Yeah, I think it would be a very easy thing to test, that you have people either look at the image they're seeing of the person on the screen as they're talking, or looking at the camera, which is very counterintuitive in some ways, which is why I have a little sticker of a smiley face there. That's great. That's a great example. Okay, I'm going to kind of continue to talk about zooming. I'm going to kind of zoom through a little of this. I'm going to come back to this. I'm going to skip this slide and go right into, this is stuff I can talk about later on in the quarter, so don't worry about this. I'm going to talk about imitation language, which is where my research, some of my research lies. There's Sophia Vergara. Just as an example of, if you ever met her, you might find yourself imitating her accent. We already discussed this a little bit. It is one of the characteristics that we do know people do imitate of each other. Imitation of accent, rate, that we do match each other's rate. We match each other's intonation. We match each other's intonation, meaning that if someone has a, kind of very large range in whether they talk high or low, we'll do that ourselves. But if someone has a more monotone voice, then we'll kind of keep our voice more in a monotone as well. Syntax, the ordering of the words, whether we use passive or active voice as we speak. And words, we will borrow each other's words, which maybe isn't that surprising in that they're already primed from what other people are saying. But it is part of the imitative process that goes back and forth. And again, we are sometimes aware. I like to bring in the accent example because we are aware of that, and we, can feel embarrassed by it. But it happens all the time, regardless of whether or not we're aware. So when Michael talks to his friend with the Texas accent, even though he's often not aware of him doing it, he is in fact doing a little imitation, and she's doing a little imitation of your dialect as well. It happens all the time, and it can be measured by various means, and I can talk a little bit about how we do that in our lab. Interestingly, you would think a social context would be needed for this to occur, but you don't need a social context. I mean, it looks like the brain's imitative tendencies are so strong that they actually will do it. Our brains will do this when we're alone in a lab, just listening to words, listening to recorded speech. And so this is how we do many of our experiments. We have subjects with headphones on, listening to spoken words from a list, simple words like table, paddle, groceries, just any words. And they're asked to say these words out loud. We don't even say, please repeat the words. We certainly don't say, imitate the words. We say, you're going to hear words. As soon as you hear the word, just say that word out loud. And then there's various ways we can test how similar that articulation of the word is to the word they're hearing. And it absolutely happens there. It happens readily. We all do this. It seems we can't help but imitate some aspects of the speech we're hearing, even if there's no social context. They're not even looking at the person. They never met the person whose voice they're listening to. They're just asked to, say words out loud. They can't help but imitate. It still works. And in fact, just as to finish off this comment, and we'll have to stop for today. This happens with speech recognition computers sometimes. I don't know if many of you have long conversations with Alexa or Siri, but what you find is that people will actually do this with computers' voices, and it causes problems for speech recognition computers because as a person talks more and more to Siri, if there's some sort of quote dialogue going on, then Siri has to kind of adjust itself. Because the person is becoming more like the computer voice, which is kind of a curious sort of thing. So again, it's not a social context. You're talking to a computer, but that imitative tendency happens automatically. It happens all the time. Okay, great. We'll finish off this discussion and then finish off our overall discussion of the computational approach next class, and then we'll start the second half of the quarter. Okay, see you guys next week.